Alright, subscribers, welcome back to another episode of Science with Surback. Today what we're going to be talking about is section 6.3, which deals with trends within the periodic table. So before we get going into the notes, there are a couple of objectives that I have for you in this video. Objective number 1, compare period and group trends of several properties. And objective number 2, relate period and group trends in atomic radii to electron configuration. Alright, so before we get into the trends, we have to understand something about atoms, and that is their radius. And so the atomic radius is the probability of where the edge of that electron cloud is. So in other words, it's a measure of the volume or a size of an atom. Now, how they measure the atomic radius is how close does an atom lay to another atom. So metals and nonmetals are a little bit different just because they do share or gain or lose electrons in some cases. So for metals, it's half the distance between adjacent nuclei. For nonmetals, it's half the distance between nuclei. Now, the electron configuration directly influences all trends that we are about to see, and the atomic size is no different. So here we go with our trend. The atomic radius is generally going to decrease from left to right. So as we move left to right in a row or in a period, it is going to decrease, okay? This is because there's more and more protons as you move from left to right. And so what happens here is as you have a more positive charge, you can pull those other additional electrons in closer and closer to that center of the atom. Now, again, all this is because we have more positive pulling power from that nucleus of the atom. And you can see our nice little trend here. Now, for the atomic size, if we talk about going down a group, the radius, the atomic radius, is going to increase as we move down a group. Now, this is caused because the energy level or those outside electrons are further and further away from that nucleus. And so you can think of this as adding layers further and further away in this particular instance. Okay, so now what we need to wrap our minds around here is what happens if we take or add to the number of electrons that we have. And if we take or add to the number of electrons that we have, we end up with a positive or negative charge. And this is the definition of an ion. So an ion is just defined as an atom or a bonded group of atoms with a positive or negative charge. What happens here? You can either gain or lose electrons to become an ion. And so what happens is that when our ions lose electrons, they form a positive charge. Again, you are losing a minus, or if you want to think about like math class, you're minusing a minus. And so what happens here is that this, if we lose electrons, allows those additional electrons to be closer or be pulled closer to that nucleus. Now, if you gain a electron, you are going to form a negative charge. Again, you're adding a negative charge. Now, as you add more and more things, it's like gaining weight, you will get larger. And so what happens here when you gain electrons is the ion becomes larger. And you can see the sodium and chlorine examples in these particular photos. So now we have to talk about the trends within the periods of ions. So ions, as we talk about positive ions, as we move from left to right, the ionic radius is going to get smaller, again, because of more positive stuff in the nucleus. And then for negative ions, we have the same trend, but notice here, I just want to point out here that the atoms that gain a negative charge are much larger than those that lose that electron. Okay, so keep that in mind as we talk about this. Now, ionic radius, we have to talk about as they move down within groups. Both positive and negative ions are going to increase, and that's because, again, you're adding that layer and you're adding that extra shell of those electrons. So you're adding more and more to the outside of that particular atom. All right, so a few more trends to talk about, two more to talk about, one of which is ionization energy. So ionization energy is saying, okay, how much energy does it take to remove or pull away an electron from an atom? And so if we remove an atom and we take it away, we are going to form a positive ion. So again, we're losing electrons, removing an electron, we're losing an electron. And it's just to say, okay, well, how strong of a hold does an atom have on its valence electron? And so if we have a low ionization, the atom doesn't really want to hold on to the electron. It's more willing to give it away. And if something has a high ionization energy, it is not wanting to give those electrons. In fact, it's wanting more electrons. All right? And so as they remove, or as more and more electrons removed, the value or the amount of energy that it takes becomes more and more and more. All right? So we can move on to our trends for ionization energy. So for ionization energy, as we move left to right in a period, the ionization energy is going to increase. As you go down the groups, the ionization energy level decreases. And again, the same reason occurs here with this trend, because as we move down a group, those electrons are further and further and further away from that nucleus, and thus it is easier to remove that electron from that particular level. All right, so now we need an explanation for why is this the case? Why do we see these values? Why do we have this trend? Well, the trend comes from the Octet Rule, which says, hey, atoms are going to gain, lose, or share electrons to try to get to 8. You see, what happens when atoms get 8 valence electrons is that they are actually filling their s and p orbitals. The only exception to this is first period elements. They only need 2 electrons because they're only filling that s orbital. Now, again, we will reiterate this, but we need to consider why some things gain electrons and why some things lose electrons. Well, the fact is here is that whatever is easier to get to 8 electrons, that's what that atom is going to do. So it's easier to lose 3 electrons than gain 5, and so that's why you see things with a positive 3 charge. All right, so this helps explain what we just talked about with ionization energy. All right, our last trend here is what we call electronegativity. So electronegativity is how strong does an atom want to hold on to its electrons. Now, what they've done here, Linus Pauling, he was a scientist, and he developed a scale for how long or how strong the electrons want to be held onto by its atom. Now, a higher number, so 3.98 is our highest, is going to indicate something that is more electronegative. A lower number is something that is not so much electronegative. Now, francium is in the lower left. This is the least electronegative, and fluorine in the upper right is the most electronegative. I also want to point out here that the noble gases do not have an electronegativity associated with it because they want to retain all of their electrons, okay? That is why we don't have that in our trend. Now, for our specific trend, we already had it there in that picture, but electronegativity is going to increase from left to right and decrease from top to bottom. Again, the reason for this is that as you move down a group, you're getting more and more or further and further away from that atom's nucleus, and you are not having as much pulling power. Now, here's again why we don't put the electronegativity with noble gases, and that is because they form very few compounds. All right, so I know we went through a lot in a very quick period of time, but that sums up the trends of the periodic table. As always, I hope you have enjoyed this episode, and if you haven't done so already, make sure you subscribe.